Okay, we are continuing with the atomic nature of matter. We talked in the last lecture about the fact that the nucleus of the atom contains protons, which are positively charged particles, and neutrons, which are negatively charged. We now go on to introduce a couple of concepts: the atomic number and the atomic mass unit. To a first approximation, the atomic number is the number of protons in the nucleus. Now, the number of protons in the nucleus should be equal to the number of electrons in the nucleus, not in the nucleus, in the atom. Because the electrons are negative, the protons are positive. So if I have 10 protons, what element would that make me? Can you tell me from the periodic table of the elements up there? If I have 10 protons, what element do we have? Sorry? Neon, extra credit to you. So if you look at this, the first row of this is the periodic table of the elements, right? Makes sense of all the elements that we have on Earth. Hydrogen, helium, that's the first row. The next row is Libabaknafni, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. The next row is Namagal subcolor, so sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And then the next one should be Kakaske Tivikraman, Fekanunkazingage, Asabukar. There we are. So you can read it off, right? So the way this is organized, if you see the blue number at the top left hand corner of each of these boxes, that number is the atomic number, which is, to a first approximation, the number of protons. So if you have an element that has just one proton, that's hydrogen with atomic number 1. If you have this element with 2 protons, it becomes helium, and it sits here on the periodic table. Now, after 2 comes 3. So let's say I add 3 protons, I use 3 protons to create this element. It gives me lithium with a 3 on top. Next, add another proton, it becomes beryllium, 4. Add another proton, it becomes boron, 5. Another proton gives me 6, carbon, and so forth until I get to 10 and I get to neon, right? Now, it turns out that if you look at the columns of the periodic table, they have similar chemical properties. They behave similarly. So if you look at hydrogen chloride, right? So chlorine ion is pretty reactive, hydrogen chloride. Yes, you don't want to be sticking your finger in hydrogen chloride, you get burned. Even worse than hydrogen chloride is hydrogen fluoride, HF. Go further down, you have hydrogen bromide, hydrogen iodide, which all tend to be acids, right, of varying degrees of strength, and so forth. So those are the rows, those are the columns. The blue number is the atomic number, which you see at the top on the slide, which is the number that designates the identity of the element. Now you notice in each of these boxes there are other numbers. There's a number that's in red. That red number is the atomic mass unit, which is the number down there, right? Which is, again, to a first approximation, it's the sum of the protons and the neutrons in the material or in the element. So here, helium, the red number, what's the red number? What number is it?
4.00.
Okay, thank you, extra credit to you. 4.002. So it's about 4. So if you look at that nucleus over there, notice that helium has 2 protons plus 2 neutrons. That gives us 4, they're called nucleons, the particles that are in the nucleus. So the red number is 4 to a first approximation. Cool? So if I look at neon, I see that the red number is 20.179. So the 20 tells me that there are going to be 10 neutrons and 10 protons. Make sense? If I look at the blue number, it tells me that's the atomic number at the top. That tells me how many protons there are. So if I give you an element that has a certain number of protons, all you have to do is just look up the periodic table to look at the blue number at the top left hand side, and that will tell me or tell you what element it is. Cool? So we've talked about atomic number, which is the number of protons, to a first approximation. Atomic mass unit, or the atomic mass number. The atomic mass number would be the red number that we talked about, which is the sum of the protons and the neutrons in the nucleus. Now, an atomic mass unit AMU is defined as, it's basically the standard unit of atomic mass, which is 1/12 the mass of a common atom of carbon, and that carbon is arbitrarily given a value of exactly 12. So if the weight of the nucleus of a carbon atom, right, of a common carbon atom is 12 units, take that weight, divide it by 12, and that will give you 1 atomic mass unit. So the mass of a hydrogen atom is 1 AMU. The mass of a helium atom is 4 AMUs, 4 atomic mass units, because it has 2 protons and 2 neutrons. Remember that hydrogen has just 1 proton. How many neutrons does hydrogen have? Okay, let me rephrase the question. How many neutrons does hydrogen have? Extra credit to you for speaking up. 1. Extra credit to you for speaking up. Let me rephrase the question. How many neutrons does ordinary hydrogen have? None. Right? But the 1 and 2, they were good guesses. Now, if you take a pure proton by itself, right, give it an electron, it holds hands, electrostatic hands with the electron, that becomes a hydrogen atom. No neutrons in hydrogen. Hydrogen is unique among the various elements in that it has no neutrons in it. Now, if I add a neutron to it, you get deuterium, which is a form, it's an isotope of hydrogen. We'll talk about this later. So it's called heavy hydrogen, and it's used in, at least in the past, I don't know if they still use it. Yeah, I think it's been used in the past as a neutron material used to slow down neutrons. So like in nuclear reactors, it is also used in trying to, like in the creation of atom bombs and stuff like that. So historically, it turned out that there was a heavy water plant in Peenemünde in Germany during the Second World War that the Allies found out about through some spy, and they ended up taking out that plant. So they bombed it into smithereens. So that whole plant, heavy water plant in Germany during the Second World War, was completely destroyed, and that was one of the key factors that put the Nazi program to create an atom bomb, set them back, and gave the Allies enough time to create an atom bomb ahead of time. Now, if Germany at that time had succeeded in creating an atom bomb before the Allies did, the world would probably be very, very different today, right? Not in a particularly nice fashion. Okay. So that is atomic mass unit. Moving on to the next slide. Isotope. Yeah, we just talked about isotopes. Isotopes are different forms of an element whose atoms contain the same number of protons but different numbers of neutrons. So here is helium. It has 2 protons, pink, 2 neutrons, neon, or whatever color that is. Hydrogen has 1 proton and no neutrons. Add a neutron to hydrogen, it becomes a hydrogen isotope. So 1 proton plus 1 neutron, this gives me deuterium. I can add a second neutron, and that gives me another hydrogen isotope. Does anyone know what this isotope is called? Is there a hand up? Nope. Okay, that's called tritium, for whatever it's worth, right? So deuterium, tritium, but they're all hydrogen because they have only 1 proton. What happens if I take another proton and add it to this? What do I get? Yep, good job. I get an isotope of helium. Notice that helium has 2 protons and 2 neutrons. So if I add another proton to this, what happens is I will end up with helium missing a neutron. So it's a isotope of helium. If I take this, right, so if I take this tritium and add 1 proton, then I get normal, ordinary helium. Does this make sense? Right? Ordinary helium is this, 2 protons, 2 neutrons. So all I have to do is take another proton and add in here. Now, from this helium, I can take away a neutron. What does this change the element? Nope. It stays helium because it's got 2 protons. What if I take this helium atom and take away a proton? What happens? Becomes hydrogen. Good job. Extra credit to those of you who spoke up. Now, if I were to take this helium atom and add another proton to it, what happens? Lithium. Good job. Extra credit. Extra credit. It becomes lithium, right? It becomes the 3rd element in the periodic table. Cool.
atom element? Does every element have isotope?
Yes. Every element, these isotopes would be of varying degrees of stability. So think of uranium, for instance. Uranium is radioactive, and typically it's radioactive because it's unstable. So what happens is it'll just randomly shoot out a neutron and say, hey, I don't like having this many neutrons. I feel like I ate too much or I drank too much, so I need to. Okay, so I toss out a neutron, right? And that's what we experience as radioactivity. I mean, you can toss out an alpha particle, a beta particle, or a gamma particle, which are different particles, which we'll talk about later. An alpha particle is a helium atom without the electrons. A beta particle is a electron, and a gamma particle is a photon, just energy. So you know that, I mean, we need to avoid radioactivity, right? Because it damages our cells, and you'll end up having kids who have 2 heads and stuff like that. And what's happening is because these particles are coming off, and they can damage the different cells in us, cause premature aging. And if the amount of radiation is hard enough, there'll be enough damage that you die. I mean, you can get radiation sickness or die immediately. Not a very pleasant prospect. Okay, so here, helium, 2 protons and 2 neutrons. So that's just a nucleus, right? So in this case, we're looking at the shell model or the Bohr model, BOHR model, or the orbital model for hydrogen. There's the nucleus, 1 proton, and they're at a distance. Remember that we said that the atom is kind of like a football field, and the center of the football field is the football, right? So that football is the nucleus, and the periphery, the outermost diameter, if you will, of the football field is where the shell is. That's where the electrons are. So in the case of hydrogen, there's 1 proton at the center of the football field. Now at the very periphery of the football field is some number of electrons that are whizzing around the football field. For hydrogen to be neutral, how many electrons do I need to put in hydrogen? 1, because I have 1 proton, right? What happens if I take hydrogen and I give it 2 electrons? Good job, extra credit. You end up with H for hydrogen negative, right? Negatively charged, because it's an extra electron. What happens if I take a hydrogen atom which has 1 proton and 1 electron, and I remove the electron? Yep. So you end up with positively charged hydrogen, right? So the positively charged hydrogen is kind of desperately seeking. It has this deep desire, this need to be fulfilled. So the positively charged hydrogen is desperately seeking for a lone electron. So when it finds a lone electron, it gobbles up the lone electron, right? And is neutral again. So similarly, if you have hydrogen with 2 electrons, now hydrogen says, I can't handle 2 electrons. And is looking for an opportunity to give away the other electron, right? That is the basis of a lot of ionic reactions, like acids and so on, behave in ways where they're trying to accept or give away electrons, and that's what they're so enthusiastic about that's why you don't want to put your finger in an acid, because if you put your finger in an acid, the acid is going to come along and say, hey, I want all of your electrons, and suck a whole bunch of electrons away from you, right? Breaking all the bonds in your hand and killing the various living cells. Okay, so there's hydrogen. Helium, 2 protons, so you need 2 electrons in the first shell. The yellow shell is the first shell. It turns out that the first shell can take, it's kind of like the Roman arena. Where are all the, usually there's a whole bunch of markers there. Okay, so think of the Colosseum, right? And think of here the lions in the Colosseum eating the plovers in the center. Now you got right? These are kind of like the bleachers, the rings of the seats. So the smallest ring of seats will have the least number of, right, available seats. So on an atom, 2 electrons can fit in here. The next ring can take more, right? I mean, in a stadium, the higher the ring, there's more circumference, so you can put more seats in there. So it turns out that the next ring can take 8, and the next ring, if I recall correctly, can take 18, and so forth, right? There's more. You can think of these kind of like the bleachers with empty spots for electrons to come and sit. And here's the nucleus in the center, right? Make sense? So this is another model that I'm presenting you to help you to understand what's happening with these shells in an atom. So the first shell can take a maximum of 2 electrons, and once that shell is full, if you add any other electrons, the electrons have to go to the next shell. And that's the reason why if I go from helium to lithium, lithium has 2 electrons in the innermost shell, so the shell is full. Add 1 more electron, it has to jump to the next shell, and you have 1 electron in this shell, right? So as I go, so 3 electrons in 2 shells, I can keep going down the periodic table until I get all the way to neon, right, which is the second row. And electrons number 3 through 10 will go into this shell until this shell has a total of 8 electrons. That means all the empty spots are filled in the shell, right? And that is why if you look at the periodic table of the elements, how many elements do you see in the first row? 2. 1, 2. And the reason why there are only 2 elements in this row is because that first shell has room for only 2 electrons. So the first row has elements that have electrons in only the first shell. The next row has elements that has the first shell and the second shell, right? So electrons are present in the second shell. So in this case, there's 1 electron in the second shell, 2, 3, 4, 5, 6, 7, 8 in the second shell, and now the second shell is full. If I add 1 more electron, right, that 1 more proton gives me sodium, so I need to add 1 more electron to keep it neutral. Now I end up starting to fill the third shell. Then I go on and start filling the fourth shell, and so on. We miss you.
So in order to get a new shell, the new shell has to be completely full?
Not necessary.
Okay.
Yeah. This is to a first approximation. Good question. So the question is, do we have to completely fill up electrons in the lower shells before we start putting electrons into the upper shells? And the answer is no. There are 2 ways that would work. To a first approximation, when we're presenting this to students, we just present the simpler model. In the simple model, you just fill this, then fill this, then fill that, then fill the next, right? But what happens is 2 different things. One is, I can send a photon to this atom and kick an electron out of the yellow shell up into the green shell. So I've got an open chair, an empty spot in this shell, and a filled spot here where there shouldn't have been a filled spot. This atom then is excited. It's got excess energy. So over time, and we'll see this later in the course, the electron can jump down from there to here and give off light, a photon. Right? That's one thing. The other thing is, as you go further up into the deeper rows in the periodic table, what happens is you don't systematically always fill one whole shell before you go to the next shell. It almost looks in terms of energies, that there's some interpenetration of the shells. So sometimes a higher shell will have a lower energy than the lower shell. Starts getting complicated. Okay? Good question, extra credit. Okay, so here's the periodic table of the elements that we talked about on the board. And again, the point is, each row of these, see the first row has hydrogen and helium, which matches the first shell being filled. The next row goes from lithium all the way to neon, and that corresponds to the second shell being filled with electrons 1 by 1, and so forth. And if you look at each of these columns, what happens is the elements that are in these columns have similar chemical properties. They behave similarly. So helium, neon, argon, krypton, all of these, they are fully satisfied. It's like a lion or like an anaconda that's just had a meal. So what happens to the anaconda after it's had a meal? Goes to sleep, right? Goes to sleep for whatever, a week or whatever, while it digests its meal. It's not hungry anymore. So these elements, what happens is they are full. They are completely satisfied. They have no desire for any more electrons. Neither do they have a desire to give away electrons. So they are completely neutral. So they tend to not react with things, right? On the other hand, the next element over, this, like fluorine, chlorine, bromine, and so forth, these are just 1 electron short of being satisfied. So these are like the most desperate to get an electron. So these are very, very reactive. Go to the next one. These are not as reactive as this, but still reactive because they're trying to see if they can get 2 electrons to get to this completely full feeling, and so forth, right? And so that kind of logic will apply as you go through the periodic table. Okay, introducing the concept of a compound. A compound, okay, this is the verb as opposed to the noun. The verb compound is basically Okay, maybe it's not a verb. To compound something, that's a verb, right? I'm going to compound something. Typically, it was applied to the old pharmacists who would basically mix up different chemicals and make a pill for you, right? In the old apothecaries or whatever. So that compounding process is the process in which molecules are created, altered, or transformed. A compound is also, and not listed there, the compound is also something like sodium chloride, where these two atoms, sodium and chlorine, are holding hands, right? So the properties of the sodium chloride is completely different from the properties of sodium or the properties of chlorine, right? So chlorine is a very reactive gas. Sodium is also pretty reactive. You put it in water, like you catch fire and stuff like that, right? So, but you bring them together, they become something completely different and benign, something that we have on our tables, right? And that we eat with our meals, which is what? Sugar? Salt. Good job. So if you look at one of these salt crystals, if you look at a crystal of salt, notice it's kind of cubic in shape. Have you ever noticed that? Right? It looks like a little cube. Have you all noticed that? If you haven't, then check out the salt at your home. Right? Take a little piece of salt and look at it in great detail. You'll find that it's kind of cubic. It has flat surfaces and so on. The reason is because the sodium and the chlorine atoms arrange themselves in the crystal in this form, where there's one sodium, one chlorine, one sodium, one chlorine, right? So every alternate atom, if this is a sodium, that's a chlorine. If that's a chlorine, that's a sodium. And they arrange themselves in the form of a cube like this, along the edges of the cube. And as they arrange themselves in this manner, as more sodium and chlorine come, let's say you're precipitating sodium chloride out of a solution, as more sodium and chlorine come, they will align themselves along this and the crystal will keep growing until it gets to the size where you can see it with your naked eye. So anytime you see a crystal, right, you go to one of these shops that sell crystals and you see not the human-made ones where they polish it in particular facets, but if you look at natural crystals and you see that they have certain facets, right, like a plane, flat plane and so on, the reason for that is because all the atoms are lining up like this. To me, that's like totally amazing. This is zillions of atoms, more atoms in one of these crystals than a billion Earths containing humans, right? So we have what, 6 billion human beings? Take a billion Earths with 6 billion human beings, get all the human beings to totally line up perfectly in rows and columns, and that becomes a crystal. If you replace humans with atoms, that's the analogy to when we pick up one of these little crystals, right? And look at it. Think of diamond, rubies, emeralds, that's what's going on. Okay, a mixture, as opposed to a compound, is a substance whose components are mixed together without combining chemically. So an example of a mixture is salt plus sand. So the salt and the sand do not react chemically. However, they're completely mixed together, right? In the case of the compound, you add the sodium and the chlorine, they react to form something new, sodium chloride. So this is a compound, whereas this is a mixture, the salt plus sand. Okay, molecule is the smallest particle of a compound. If you split the molecule any further, it will split up into the elements, and the properties of the element atoms, which is what you have now, would be completely different from the property of the molecule. So here is an oxygen molecule, oxygen holding hands with oxygen. Here's an ammonium molecule, nitrogen holding hands with 3 hydrogens. Or a methane molecule, carbon holding hands with 4 hydrogen atoms. Or a water molecule, right, like Mickey Mouse head. Oxygen molecule with the 2 ears. The ears are the hydrogen atoms. So each of these is a molecule. Now if I split this further, I'll end up with an oxygen atom. Chemically, I can split this further into 2 hydrogen atoms and an oxygen atom. But their properties are different from this combined unit. Okay? Okay, introducing a chemical. You all know what a chemical reaction is, right? Chemical reaction is you put 2 things that react together and they react and they form something new. So here is an illustration, if you will, of the fact that, now do not do this experiment at home, right? You'll probably blow yourself up and burn the house down. Car battery attached through a wire to a metal probe, the other end of the car battery again to a metal probe, and this is being fed into, I wish there was a way to shut this off. into a glass of salt water. And what happens is, once you have the current flowing, you end up with bubbles at each of these electrodes. And you could collect those bubbles, and this would be oxygen and that would be hydrogen. Right? So this is making the point that you can take the water here and split it into hydrogen and oxygen. And it's typically something like this that is done to create hydrogen and oxygen for oxygen and hydrogen tanks, right, that you can purchase. The reason why you don't want to do this is you'll probably blow up the battery. Now, if you take these two gases together separately and you ignite them together, basically the oxygen will burn the hydrogen, if you will, to form water, which is what you do. Many rocket propulsion systems use combinations of hydrogen and oxygen react to create water. Okay, next concept is quantum mechanics. Quantum mechanics, I think I mentioned that this is what, to a first approximation, that's what I have done for most of my research, my career life as a scientist, is dealing with quantum mechanics, quantum physics, and the applications of these, either in semiconductor devices or with electron microscopes, and using those properties. I mean, taking electrons, flinging them at things, converting the electron, which is a particle, into a wave because you fling it fast enough, then look at the interaction of the wave with the material, and based then on the interactions, you can tell things about the material, right? So quantum mechanics is a theory of the small scale world where things behave very differently compared to the macro world, which is the world that we live in. What happens is particles start behaving like waves, where it's along the lines of you, if you look at you, you seem to be all matter, and you seem to be all like particles. If you travel fast enough, you will start behaving like a photon, which is really weird. Now in reality, we cannot gain enough energy to travel fast enough for that to be appreciably noticeable, right? But we are able to take small particles like protons and neutrons and electrons and so on, and accelerate them, move them at speeds that are a significant fraction of the speed of light. And when that happens, you start seeing these particles behaving no longer just as particles but as waves, which is amazing. And we may see that in a future lecture. Okay, introducing a couple of other concepts. Antimatter. Now, it is believed that every particle in the universe has, okay, I have to be careful of how I say this. Every